Good morning, class. It's about 10:43 a.m. on Friday, March 27th, and this is the first of the recorded lectures since classes have been suspended, at least class meetings on campus. So I want to go ahead and get moving and keep working our way through the material here. This presentation is going to pick up at where I left off on the last lecture. We started control valve sizing discussion on the last class. Or I'm sorry, my last recorded lecture, which I have already sent to you. I'll probably attach the link to the email that has this one as well to make it a little bit easier for you to find. But so we did discuss this slide that's shown on the screen. And let me go to presentation mode here. There we go. So this one has already been discussed, so I'm not going to go back and redo it. So you need to, you'll catch this at the end of the previous video lecture. Okay, so this slide is discussing direct return piping systems on, say, a hydronic system that has multiple rooms or spaces that are to be conditioned, and each space having its own air handling unit and coil. Let's see, do we have a picture? Yeah, so that's that gives you some kind of an idea. I'll jump ahead just for a minute so you can see the picture. Okay. So just some comments about direct return, when it might be used, or some of the considerations. Even though the GPM requirements could be the same, i.e. here, these could be 7 identical offices with the same load, could have the same unit installed. The circuit pressure drop differentials vary, as no 2 circuits are the same length. And that's looking at the piping length. So if you look at one over there from the pump, it has a very, very short length of piping before the coil takeoff. That's reverse return. Let me see. Let's go back. This is direct return. I'm sorry. And so you see the supply piping is short. You come out of the unit to the return header, and it's just right by the pump. And so that's a very, very short circuit. If you compare that and contrast it with number 7, the supply line is extremely long and the return line is extremely long. So even if the units are identical and the pressure drop for each circuit, once you pull off of the supply main and return main, is identical, that the circuit is, the pressure drop is going to be huge for 7 and almost nothing for 1, and it will increase, you know, consistently from 1, 2, 3, 4, 5, 6, 7. So I mean, that's obviously an issue. So what you got to do is you put in balancing valves, and the balancing valves goes in each of the little subcircuits, 1, 2, 3, 4, 5, 6, 7, and is just an adjustable flow resistance so that you can try to balance each one of those out to have the same total pressure drop. But as circuit length increases, you know, and another impact would be that the pump head increases, because you've got to have enough head on the system to push the desired flow all the way through number 7. And so as you have more and more and more of these zones, that pressure is going to go up. So you have to crank up the pump head, or select a pump that has a high pump head, to get it to 7. But then what do you do at 1? Well, you have to crank that balance valve almost closed. And so that increases the velocity through that valve, which can cause noise and potentially damage the valve because of the high velocities, because you got it cranked almost closed. So direct return, while it can be used, can cause some problems that you have to be aware of. Okay, so one thing you can do, one solution to that is let's buy a little extra pipe. And so this shows a two-pipe reverse return system. And generally it's preferred over the direct return system, as it basically is pretty much self-balancing as it tries to equalize the pipe length on each one of those circuits 1 through 7. And so now if you look at it, and this is relative, say, to the pump, the supply piping from the pump to number 1, again, is very short, but the return piping, you come out, and where it connects into the return, you go all the way down to the end and then turn and come all the way back. So for circuit 1, it has a very, very short supply pipe, but a very, very long return pipe. So, then you can move down to, say, zone 4 on this thing. And so it has a longer supply line, but a shorter return path than compared to 1. And then if you go all the way down to 7, it has a very long supply line and a very short return path. So the piping lengths are relatively close, which makes this thing want to self-balance. Now that's assuming that the coil drops 1, 2, 3, 4, 5, 6, 7 are all the same or pretty close. And so that's the second bullet down here. If a design requires varying flow rates through coils, for example, and now these don't have to be the same size zones. 1 could be an office, 2 could be a classroom, 3 could be a lab, etc., or just whatever in a building. So maybe number 1 requires 50 GPM, number 2, 90, number 3, 30, etc. But what you can do is you can try to design that zone 1 pressure drop to be the same as zone 2, zone 3, zone 4, zone 5, etc. Okay, so if the piping lengths are approximately the same and the pressure drop from the takeoff through the coil back to the return header are all about the same, then this system is going to be pretty much self-balancing. And that's what we're hoping for. Not exactly, you'll still require balancing valves, but you won't have to, crank one almost shut and have another one completely open. So that's a characteristic of a reverse return system. Okay, so there are multi-type piping arrangements, and this shows, let's see, so we've got our main distribution lines from the pump, the supply, and then the return. That's a reverse return on the distribution header, but then the risers are direct return. So we got reverse return, distribution piping, but direct return risers. And there's some, we'll talk about this further on another slide, but just take a look at that and convince yourself that the words that I'm saying do, go with this system. Okay, so we see this a lot of times in apartment buildings as the direct return arrangement on the riser simplifies the piping, because otherwise you got a lot of times fairly small chases running vertically up through that. You might have a 3, 4, 5-story building, high-rise apartment building, and it's awkward to run that reverse return in a fairly small chase, if that's the case. But the two-pipe reverse return main distribution piping tends to balance the overall distribution between the risers, and that's a good thing. Makes it easier on the test and balancing guy. You don't have to crank the balance valve shut as much, etc. Okay, so that's a little more discussion on that. Now, let's look at some of the design parameters here. So, in order to limit flow imbalance, with this arrangement, the pressure drops on the individual circuits, and the individual circuits on the top one, it's the circuit from A to B. On the middle one, it's A1 to B1, and the bottom one is A2, B2. And what we're saying is it should not vary by more than 25%. So let's say if A to B is 20 feet, then 25% of 20 feet would be 5 feet. And so A1, B1, and A2, B2 should not be less than 15 or more than 25. And you would like them to be as close together as possible because that helps in your balancing. Okay. And another requirement would be that 25% should be designed at a high percentage of the total riser circuit pressure drop, i.e. the pressure drop from AC plus BD plus AB. So that's the total. That's the longest total run. So that would be the largest of the circuit pressure drops. And what that does is, so what that means is that the pressure drop from C to A on the supply side and from B to D on the return side is minimal. You try to minimize that, but we do need to stay at the 2 feet per second level or slightly above to move air through the system. So you've got kind of competing design interest here, but you don't want, other than respecting the 2 feet per second, you don't want the drop from AC plus the drop from BD to be very large, and certainly not be a large percentage of the total drop. And we'll have some more parameters on this in just a second. Okay, so, and again, that helps to balance because you're concerned about getting water out to that end circuit at the top of the building, AB. Okay, so the riser pressure drop, as I said on the previous slide, AC plus BD should generally not exceed 50% of the subcircuit drop. So if AB is 20 feet, then 50% of that would be 10. So the pressure drop, AC plus BD should be 10 feet or less in order to help with the balancing of this, excuse me. Or another way to say it is that the pressure drop of AB or A1B1 or A2B2 should be approximately twice that of AC plus BD. So it's saying the same thing from the other direction. Okay, so I would recommend that you kind of write out these requirements, and because this is what the design engineer has to know in order to be able to easily and effectively design a piping system and get it to work with minimal problems. The last thing you want is to have all this pipe strung out through the building and then have to come back in and make modifications to it because the design is not correct. Okay, pump selection. Correct, pump selection is needed to establish system balance. They want, and now these comments are for a throttling valve type system. These days, you probably are going to have a variable speed drive, and so I think this pump curve, the shape of the pump curve is not as critical in a system that has speed control. But nonetheless, this is good general information to have. The pump should generally have a flat curve, and the selection should be in the area from the center of the curve to the left portion of the curve. You want to get away from that deadhead situation or at the minimum flow rates. Flat curve along with good control valve selection helps to establish a stable control. Selection to the center left will enable the pump to drift to the right on its curve, which will aid in overcoming system imbalance. You see in the figure on the right, what happens is you're not very flexible and you can get into unstable operation with that steep pump curve and control valve, because as soon as that control valve makes a move, it drives the system pressure too high or too low, depending whether the valve opened or shut, and that can lead to instabilities. A little more of the same, just kind of shows that, your design point is kind of in the center and you've got kind of a minimum flow that you expect and a maximum flow. And the pump needs to be able to accommodate both of those. Okay, flow rate variation. Okay, two basic methods can be used to accomplish coil output control from the water side. Okay, and so that's the amount of heat or cooling that's accomplished at the coil. So, well, we can do it two ways, or a combination of those. We can adjust the water temperature. So if you're in a heating situation, maybe you put in 140-degree water when it's not too cold outside. And when it's really cold, maybe you put in 160, 180-degree water, and that works. That works really well. The other way you can do it is with water flow variation at constant temperature. So, maybe it's and it is much simpler, as we'll see, and cheaper to just pick a water temperature uh, and then vary the flow rate. Just a simple valve can throttle back and forth and adjust the water flow in order to adjust the capacity on the coil. And it's possible to design a system that would incorporate both of those, even though the expense would probably be considerable. Okay, so each control method has definite advantages, and it's up to the design engineer to select what he wants and keeping a reasonable cost in mind. The establishment of design flow rates is the first necessary step. And where does the flow rate come from? That comes from the good old carrier hat program or train trace. When you do your design simulations on the building, that's where you get your loads. You run that thing, you do your design. It says, okay, the worst case scenario on this zone is, 9.3 tons. So you say, well, I'm definitely um, I'm definitely looking at a 10 or maybe a 12 ton coil if 9.3 is my max cooling load. So I will probably be just a little bit above that. And that cooling load based on your expected temperatures will give you your design flow rate. So, hopefully y'all have done enough of this now that this is starting to make sense to you. Okay, well, this is a very interesting slide. So we'll take a minute to talk about this. This shows the influence of flow rate on system performance. And this is for, let's, I guess, 20 degrees. That would probably have to be a heating system. Most cooling systems don't have that big a delta T. So this would be for a heating system where we've selected the coils at design condition to give a 20-degree drop in water temperature. Okay. And so look at that. So, at 100% of design flow rate, well, we get 100% design heat transfer. Well, that's good. Full flow, full heat transfer. Well, at zero flow, you get zero heat transfer. Look at 50% flow. 50% flow, we still get 90% heat transfer. Whoa. Whoa. 50% flow, 90% heat transfer. What if we're at 80% flow? Well, we've hardly cut the heat transfer at all. So your valve, has moved significantly you've cut the flow rate 20%, and you basically haven't hardly adjusted the amount of heat that's going in the space. And then on the low side, what if you went from 10%, at 10% design flow rate, we're still getting 50% of the heat. So what if you go to 5? At 5%, you're down to 30%. So then a very small adjustment makes a huge change. So you see where with this characteristic on a valve would be challenging to try to adequately control space temperature. But we have other types of valves we'll see as we go forward. But this is flow. This is not a particular, this flow variation is caused by a particular type of valve, but that's the flow variation versus heat transfer. So these are more comments on it. I've probably run ahead and already said everything. So variation in design flow rate down to 50% have small impact on the overall heat transfer. But when you get to the low end, well, we'll see what's happening here. What causes this effect is, let's say if you cut the flow in half, you double the residence time for the water in the coil. And so then the delta T on the water goes up because it spends twice as much time in the coil. And so you get more heat out of it. And so if you plotted the leaving water temperature, that 20-degree delta T at 50% would probably be 40, or which means that you would not quite, it's not quite linear, but it's going to go up significantly, which is why the amount of heat transfer stays up as you cut the flow rate. Okay. So flow rate variations must be significant from the design point to make a meaningful change in heat transfer rate for a 20-degree F delta T system. If we've got flow imbalance, coil receiving less than design flow rate, could be, if the flow imbalance is bad, even with the valve in the wide open position, you could be down at 30% design flow, in which case that thing is going to be jumping all over the place. So issues. Okay, but now look what happens. So if we design a system for a 40-degree, 60-degree, etc. Delta T, then the curves start to flatten out. And that's because at 40-degree delta T, the water is already spending quite a bit of time in the coil. And so as it slows down from there, you don't get as much additional heat. And at 60 degrees, it's not spending much time at all. And so the curves become more linear as the delta T increases. Now, increasing delta T on a coil also has impact on, controllability. And so we'll get into more discussion on this later, but there's lots of, whatever decision you make, it has lots of different ramifications on other aspects of the system. Okay, so heating systems designed on a high temperature drop, low supply water temp basis, and chill water systems designed on a high temperature rise, high supply water temperature basis are especially critical in terms of controllability. These types of systems must be designed with care to ensure design flows in the terminal units in order to obtain stable control. Okay, let's move on to temperature variation. Wow, look at that curve. That looks pretty nice. And it is. So the heat transfer ability of a unit is directly related to the temperature difference between the air side and water side of the unit. Variations of water temperature represents an effective and accurate method of heat transfer control. So this actually works pretty darn well in the field. Water temperature control should be used whenever possible, as it offers a relatively accurate method of control. Problem is, it costs more than flow control. It's harder to control and requires more expensive control equipment than controlling at a constant delta T, just controlling the flow rate, because that's just a simple throttling valve, a simple control valve. It can be two-way or three-way valve, and it's easy to do and cheap. So whereas the temperature control may be the best, most of the time you're not going to be able to do that because it's going to cost too much. Ain't that the way life is? Temperature control is seldom used as a terminal unit control method. Simple valve control of water flow is generally less expensive. There you have it. the almighty dollar rules the day. Okay, just a few comments about two-way control valves. Two-way control valve is constructed in two basic types. The single-seated valve is most common, which looks like this. You can have modulating, which means it can an infinite number of set points, and you can adjust the flow, or you can do two position that snaps either open, full flow, closed, no flow, back and forth. Okay, the modulating valve is constantly moving up and down in response to the demands of the thermostat, usually. They're installed with the flow direction opposing the closing action of the valve. So now you don't want to get these things installed backwards, because then the inlet flow is trying to slam the valve shut and it doesn't work so well. So, you know, they all have little arrows on them. So if you're out in the field, you need to know where the pump is, what direction the flow is going, and check some of the little arrows and make sure that the flow is going the right direction, or you're going to have some banging in the system as these control valves get slammed shut by the flow. There we go. So that differential pressure, that valve closing against the flow coming in, it prevents slamming the valve closed, causing noise and water hammer in the system. Okay, the double-seated two-way control valve is generally recommended when high differential pressures are encountered. As flow goes through this valve, it tends to open one port while trying to close the other, so you get kind of a balanced thrust condition, which lets the valve operate smooth without water hammer, regardless of differential pressure. So that's a good thing. However, if you need really tight shutoff, it's not recommended, because you can get thermal expansion on the stem, and it may, depending on how that works, it may slightly want to open one of the seats and it may leak a little bit. So if your heating system should be checked carefully on basis of the flow heat transfer graph. You got to be a little careful with them. Okay, we have three-way valves, and they make two varieties: the mixing valve on the left and the diverting valve on the right. And you see on the mixing valve, we have two inlets and one exit. And on the diverting valves, we have one inlet and two exits. And they can, either one can be employed in a system. It just kind of changes the piping a little bit. So you want to make sure that the valve shuts off in an opposing direction to the flow pattern, to, again, like we talked about on the previous slide. So this is what the piping arrangement looks like. On the left, we've got the mixing valve, and so the supply comes in, and there's a bypass. This would be for a three-way valve. Now, a two-way valve is just gonna pinch off the flow, you know. But so this is in a three-way arrangement. So the supply comes in, and it's got a bypass line, and it's got the line going to the coil, and so that puts two inlets and one exit, and then the valve simply rotates the amount of flow from the coil to the bypass, depending on the instructions from the thermostat. On the diverting valve, you have one inlet, two exits, so it puts the valve on the other side of the coil. The operation through the coil is about the same. You can use either. In terms of keeping air out of the coils, which one of these would you recommend? This is a great true, false, or multiple choice question. Well, remember, when we have a pressure drop, we can liberate dissolved nitrogen probably from the water flow. And so if we put that valve on the back side of the coil, on the downstream side of the coil, then that air liberation would go into the return line, And if we have 2 feet per second, then that air would hopefully get brought back into the return header, return distribution piping, and make it back to the air separator and get pulled out of the system. So if we have it on the diverting valve side on the right, then that air could go into the coil, and it's possible it could get caught trapped in the coil and eventually could cause us problems. So between these two, I would be selecting the mixing valve, and I think that you probably should as well. Okay, installation of mixing valve, diverting valve related to a boiler. So you can put them on either side. So we see the mixing valve is on the discharge side, which I think that would be my choice, because again, any air brought out of solution based on the pressure drop of the valve would go directly into the air separator and get pulled out, get controlled. That looks pretty good. On the diverting valve, the air could bypass the boiler, depends on the position of the valve with that flow and the bypass, or it could go into the boiler, in which case it would probably get separated as well. So I suspect both of these would probably work just fine, even though I personally would go for the mixing valve, I think. Okay, some comments about valve location. The relative location of the air separator and control valve should be noted, as this arrangement allows full system flow to pass through the air separator. Yeah, so like say that bypass line, you would not want to tie it in between the air separator and the pump suction, because then air that went through there would not, or air and water that would not go through the air separator. So you want to be a little careful about that. And you see the air separator location right on the suction of the pump. Remember, that's the location, the point of no pressure change. And so that means that that pump head is going to be added to, it will be cause an increase in pressure on the discharge side of the pump. So that's good. So the high pressure control valve should never be placed between the pump suction and the point of air separation, because then you'd have a additional pressure drop going into your pump. So that's all good fundamental stuff that you need to remember if you ever get into a design situation. Okay, so I sent you an assignment working with valve, calculating valve flow coefficients and working with those equations, which are much more detailed than this. This is the simplest version of this. It doesn't have the geometry correction factor or anything, so that this equation written as is, Q CV times square root of delta P over specific gravity, would be for a system where the inlet exit pipe and the valve were all the same size. And of course, from the assignment, you see how to handle different sizes, and hopefully you have, or you will be writing your creating your Excel sheet to program in those coefficients, like I asked you on the previous email. So anyway, so you can see how the CV changes. A higher CV means basically the valve can pass more flow at the same pressure drop. So, a bigger CV is a bigger valve if it's at the same position. So if you look at the 100% position, and we'll see this in a minute, this valve could pass about 540 GPM with a 1 PSI pressure drop. That's kind of what that means if it's standard water. But anyway, so you see how that CV changes as a function of the percent open position on the valve. And I'd also note the units, GPM divided by PSI differential to the 1/2 power. obviously US units. Okay, CV ratings, this is, I probably have run through this, but we'll look at the bullet points. Valve sizing, we generally use the CV rating that comes from the manufacturer. They do these by testing. The strict definition of CV, CV rating on a valve is the numerical value that corresponds to the flow rate through the valve at a 1 psi pressure difference, pressure drop across the valve. So a valve with a CV of 10 would have a pressure drop of 2.31 feet or 1 psi when 10 GPM is passing through it. And just know 1 psi is 2.31 feet of water, and that comes from 144, and that's what, square inches per square foot, divided by 62.3. That's the density of standard water. And what is that? That's pounds per cubic foot. Yeah. Okay. Higher CV, the lower the pressure drop for a given flow rate, for a given flow rate in a given valve. As an example, assume a design requires a valve which will produce a 12-foot pressure drop at 40 GPM, and so you can solve the valve equation. Like we're showing there, 40 divided by the square root of, that's 12 feet. We're dividing by 2.31 to get it into PSI, and we're assuming the specific gravity is 1. Now, if you had different size pipe and different size valves, you would have to include that geometry factor to do it correctly. These slides don't get into that. You know, these slides are more fundamental than that, but that's why I gave you that assignment, so that you would realize that this is a stripped down version of this valve equation. The same valve body can have different CV ratings. They can change the port sizes, and I think that may have come out of that video a little bit as well, but we'll have some examples in here. We'll work through a bunch of examples toward the end of this presentation. So you'll get very used to working with the CVs. Okay, so control valve seat plug configurations, there are 3 different basic types of seat plug configurations. There is a quick opening, there is a linear, and there is an equal percentage. And you can read those definitions. What you really need to understand is the curves on the next slide. So I'll let you just read those definitions on your own. Okay, so here you can see that the quick opening, it kind of looks like that flow that we had on the 20 degree delta T coil. But anyway, so this is slightly different, but this is percent of full valve stem travel versus percent full flow at a constant pressure drop. So these are put together by the valve manufacturers. But you can see at that 50% position, that quick opening valve is 90% flow. And so you've really got to close that. So you've closed the valve 50% and you only reduce the flow by 10%. So you see, you've really got to close that thing a lot. And so quick opening would really, the name refers to when the valve is closed and you open it, you don't have to open it very much in order to get a significant amount of flow into your coil or wherever that flow is going. Linear attempts to be 50-50, and equal percentage is just kind of the flip or the opposite of quick opening. If the valve is shut, you open it 10%, you don't get hardly anything. You open it 50% and you only get 10% of flow. And then you open it 90% and you're up to about 56, 57%. So you just have to make sure that you understand when you spec a control valve, what sort of seat plug configuration and how does that factor into the controllability of your design. And this, again, shows that flow rate variation and the amount of heat transfer that you get. So really, you need to reflect on the valve characteristic and how it's going to affect the heat transfer, either the cooling or the heating capacity that's going to be occurring in the space, and that your system, your control system, can adequately control your space temperature. Okay, I think I'm going to stop here. This gets into a little bit on pump operation, and I've got some other slides, another presentation I'm going to pull up, but I don't want to run these videos just too long for you, so that you can maybe have a few more videos but not have to stay with that same video for as long. So I'm going to stop this one right now. So y'all can wake up now and I'll post this to you, and we'll do this again shortly. So I hope you guys have a great weekend, and I'll be back in touch. Next thing I'm going to do is a homework assignment. That's on my list for this afternoon or this weekend, and I'll get that out to you shortly. So I'll be back in touch. Bye.